All right, silly people, here's the situation. We have this covariant expression here, which is apparently the covariant equivalent of Ohm's law. That is, the current density of a medium is equal to its surface charge density times the electric field E acting on it. And so what we're going to do is I'm just going to mess around with this equation um, and make sure that it does end up looking like this. And making note of the fact that we have some quantities that we should probably define. J alpha in its own rest frame, so I'll say J alpha prime, is just going to be C rho prime for the time component, and then all the spatial components are the vector J prime. Um, and then the 4 vector for velocity uh, in the thing's own rest frame is literally just C0, right? Because it's not moving. Um, and so we also get the covariant form of this for free uh, because we're working in the mostly negative uh, framework. So yeah, time component doesn't get switched in sign. So we have all that stuff. Um, so I am just going to wrestle with this equation by writing everything in terms of row vectors and column vectors. So J alpha is going to be C rho prime, JX prime, JY prime, JZ prime. And then we're going to have minus 1 over C squared. There's an inner product that we have to do between the 4 vector, which I'm going to write as a row, C0, 0, 0, and then the 4 current as C rho prime, JX prime, JY prime, JZ prime. And then it's all multiplied again by the 4 velocity. This time I'm going to write it as a column, and then it's going to be C rho, no, it's just going to be C 0, 0, 0, right? But then on the other side of the equation, we have the strength tensor times sigma over c. So we have a strength tensor here, which is going to be, I'm just going to write it all out, ex, ey, ez minus ex 0 bz minus by minus ey minus bz at 0 bx minus ez by minus bx 0. And then with primes on all of that, because all of this is supposed to be representing the fields in the rest frame. So there you go. And then it's contracted with the 4 velocity, the row 4 velocity. So it's going to be C 0, 0, 0. All right. So rewriting the left side of the equation, I'm not going to change this stuff yet. But then I have a 1 over c squared, and then I'm going to do that inner product. So we're just going to have c times c rho prime, so we just have c squared rho prime. And this is multiplied by the vector c0, 0, 0. And on the right-hand side, we have sigma over c. And then because the u alpha is a row vector, what we're going to end up with is just e prime times c, right? Because we're just going to go down this first row, multiply it by c each time. So yeah, we just get c e prime. So simplifying a bit, we have c rho prime, jx prime, jy prime, jz prime, and it's going to be minus C rho prime 0, 0, 0 equals sigma E prime, and then you could just do that subtraction, and you get J prime, the vector, is equal to sigma E prime. And that's pretty cool. So yeah, we did recover Ohm's law from all that. Now we're going to actually move the thing. We're going to move the thing with the velocity c beta. And so u alpha actually has values in it now that aren't 0. So we have to redetermine what those are. So u alpha in the moving rest frame is going to be gamma c gamma times the velocity 3 vector. And so we already have the velocity 3 vector, so it's gamma c comma gamma c beta, and I'm just going to write it as gamma c 1 beta vector. So that's pretty cool. Interesting to note that now that we have a spatial component, the contracted version of this is going to flip the sign of the space component. So it's going to be like that. Okay. So we have to find that we can represent the current the 3 current in a specific way. And so first of all, it involves this dot product here, u beta j beta, just from the equation that we had up top. In this scenario, this is going to look like gamma c over c squared, and then we have the rho 1 beta vector, but it's the minus beta vector actually because it's contracted. And then we have the column current for current. So we have c rho here, and then the j vector there. Right? So taking the dot product of those, we get gamma over c, and we get c rho minus beta dot j. And that's pretty interesting. And we're going to use that result a lot. So looking back at our main equation, I'm just going to write it again to avoid confusion. It's j alpha minus 1 over c squared u beta j beta u alpha, and then there's a parentheses here, I think, equals sigma over c f alpha beta u sub beta. I'm just going to look at the alpha equals 0 components, so time components only. The time component of the current, the forecurrent, is going to be c rho. That dot product we just calculated as gamma over c times that junk. So we have gamma over c rho minus beta dot j. And this is multiplied by u alpha, and then the 0 component of u is just gamma c, so we have a gamma c here. And then on the right hand side we have sigma over c, and then this is going to just be running across the first row of the strength tensor, which is the negative e vector. So we have minus e, and we're dotting it with the contracted 4 velocity, which goes like minus beta times gamma c, so minus gamma c beta vector. So we're going to simplify this a lot. We're going to say c rho minus, and then we're going to have gamma squared c rho. We're also going to have a minus gamma squared beta dot j. And then on the right hand side we're going to have sigma over c. Actually, the c cancels out. We just have gamma sigma E dot beta. Okay. Um, we can actually simplify this expression because we have C beta times 1 minus gamma squared, right? And actually this should be plus, I just noticed. This is gamma sigma E dot beta. And 1 minus gamma squared equals 1 minus 1 over 1 plus beta squared, which is 1 plus beta squared minus 1 over 1 plus beta squared, which is beta squared over 1 plus beta squared, which is beta squared gamma squared. So we have C rho beta squared gamma squared plus gamma squared beta dot j equals gamma sigma E dot beta. And we're actually going to solve this equation for gamma squared beta dot j to be plugged in at a later time. C rho beta squared gamma squared. Yeah, we're going to use that in a bit. Because now we're going to look at the space components of this equation all the way up here. So we have ji minus 1 over c squared u beta j beta ui equals sigma over c fi beta u beta. And we're going to just tackle this equation one side at a time. So first of all, we have the solution for the dot product up here because it's gamma over c times that junk. So let me just copy that result down here. Right, that is going to be u beta j beta. Yeah, that's a u. So just going to plug that in down here on the left-hand side. We have 1 minus 1 over c squared. And then this is gamma over c. No, because this is already 1 over c squared. So we have just gamma over c. C rho minus beta dot j. And this is ui here. And that's, I'm just going to leave the right side as it is for now and get back to it in a second. We know what the space components of ui are because they're just gamma c beta vector. So I'm going to actually write that out. So gamma over c rho c beta dot j, and this is going to be gamma c beta vector, but indexed to the ith component, so I. Right. And then we're going to just simplify this term a little bit more because it's going to be gamma squared rho c minus or plus gamma squared beta dot j, all of that times the I component of beta. And we happen to know what gamma squared beta dot j is. So we're going to plug that result in there. So we're going to have gamma squared rho c plus gamma sigma e dot beta minus c rho beta squared gamma squared. And this is the I component of beta right there. So interestingly, we again have some interesting combination of gammas and betas attached to the rho c term. So I'm going to collect those up. and then this minus sign should be in here. Yeah, that makes a lot more sense. So gamma sigma E dot beta, and then we have minus rho C, and then in here there's going to be gamma squared plus beta squared gamma squared, right? And that's the term which we are going to try and simplify. So we got 1 over 1 plus beta squared plus beta squared over 1 plus beta squared. So we truly just have 1 plus beta squared over 1 plus beta squared. So it's 1. That's so cool. We're going to just say that now this is Ji plus gamma sigma E dot beta minus rho C. Yeah, that's multiplied by beta I. Now I'm actually going to sum over I on the left side of the equation, so now we have the 3 current here, so that plus gamma sigma E beta, and let's actually separate these because I want it to be beta vector times gamma sigma times E dot beta and minus rho C beta vector. And we know that C beta was the definition of the velocity vector, so we're going to collect it into the velocity vector as well. Right, so just rho v. Okay, now we have to do the right side of the equation, which, reminder, was sigma over c f I beta u beta, but then we're going to end up summing over I. So I'm going to grab my strength tensor that I wrote down before in painstaking detail. This thing is a pretty nice thing to have. And since we're only summing over the spatial components, we can pretty much neglect anything that's going to come from the top row. So the right-hand side is looking like sigma over c, and then it's going to have f 1 beta, so the second row, times u sub beta, plus f2 beta u beta plus f3 beta u beta. So we're going to end up with a total factor of the vector e, right? So we have e times, and then the time component of u was gamma c, and then we have bz times uy, by times uz. So okay, it's the cross product of beta with b times gamma c. So plus gamma c beta dot b. Okay. Funky stuff. We'll factor out a c from that. So we'll have sigma gamma times e plus beta dot b. Or not dot, it's cross. I miswrote it before. It's cross b. Alright. Putting it all together, we have j plus beta vector gamma sigma E dot beta minus rho V equals sigma gamma with an E plus beta cross B. We're going to collect all those terms, solving for the 3 current, and that's going to be, it's going to be a big term. We're going to have a bunch of terms inside this sigma gamma. We have the E from before, and we have the beta cross B from before. But then we're also taking a minus, no gamma this time, beta vector times the dot product of E with beta. Right. And then also adding on rho V. And I think that's even what Jackson got for this part. Yeah. Okay, that's what Jackson got, so we're good. Then the next bit is talking about what happens if we let the density, the charge density in the rest frame go to 0. So what is actually the charge density for the moving rest frame? So that's kind of interesting. If we write this equation one last time, but then only look at the primed components, so lab frame, minus 1 over c squared u beta prime j prime beta, and then this is going to be u prime alpha equals sigma over c prime alpha beta prime beta. If the for velocity, okay, so in the rest frame, the for velocity we already said was 0, or actually c times nothing, and then the 0, 3 vector. And then we're setting the current density for vector, so the for current. Usually there would be a rho prime times c in the time component, but we're setting rho prime to 0, so that's 0, and then this is the vector, 3 vector j. So if you take a dot product of these, you're just going to get 0. So actually we just have j alpha equals sigma over c f alpha beta u beta, right? And so just looking at the time component of this, we're going to have c rho equals sigma gamma, and then we already kind of did the time component of this before, actually. So it's E dot beta for that. And we can rearrange that to be sigma gamma over C E dot beta. But then also looking at the space components of that, we have the 3 current on the right, on the left side, I mean, and we also already did the right-hand side for the space components, and we ended up with sigma gamma E plus beta cross B. So yeah, if rho is 0 in the rest frame, then you get this charge density and this current density in the moving frame. So that's pretty interesting. All right.